Welcome to the ECEDHA Summit Series. My name is Tom Costello from ECEDHA, and we're going to deal with exploring the maker approach to embedded microcontrollers in engineering education and industry perspective for the next 2 hours. So I thank you for joining us. Thank you for your interest. And Elizabeth, maybe we could just move on to the next slide.
Yeah.
Okay, and in particularly want to thank the Makers Program sponsors. These are the key to the success of what we do with the Makers overall. And thank you to DigiKey, thank you to Infineon, and thank you to Microchip for their dedication, involvement, support. And I can't say how much ECEDHA thanks you, and of course the corporate members, of which the number continues to grow. And these are key to the heart and soul of ECEDHA in terms of helping us shape the programming and being involved in speaking opportunities, demonstrating their products and services through the exhibit process and financially as well. So, ECEDHA wouldn't exist without the support of our corporate members. So we greatly appreciate each and every one of them, for sure. So, and this is just a couple of housekeeping things. And please keep your mics muted unless you're speaking. And then utilize the chat feature to ask questions or exchange ideas rather than interrupt the speakers as they go through the next 2 hours. So just go ahead and use that chat feature. And at the end, we'll see what we can cover. One way or another, we're going to take care of your questions. So fear not there. So the next is, I'm going to turn this right over to YC Wang from DigiKey. And he's the director of global academic programs at DigiKey Electronics. And he's a super guy, super support. So YC, go ahead and take it away.
Okay, thank you so much, Tom. And thank you to our esteemed audience for taking your time today to attend this webinar. My name is YC Wang. As Tom mentioned in the introduction, I run the DigiKey Global Academic Program. And there are multiple components to DigiKey's outreach into academia, and Maker is a big part of it. We believe that engineering curriculum around the world should involve some aspects of hands-on electrical engineering projects. And we are very happy to have universities from around the country today talk about their experiences in setting up their makerspaces. And we have also invited Kevin Walseth, our maker guy at DigiKey, to talk about the process of setting up a makerspace if you are thinking of setting up a makerspace on campus, in your office, or at home. And in addition to that, we are also very excited to have Microchip lead a discussion on the creation of a maker-based curricula based on a top-down, hands-on approach. So we will now lead into the first segment of our presentation. Thank you, Tom.
So we're going to go ahead and introduce that. The next speaker is a DigiKey speaker, correct? Or who are you leading each one of those folks from their respective makers in introducing them?
Actually, I'm trying to see the slide, Tom. I'm just seeing your face.
Okay, Elizabeth, you want to put that next slide in that follows the agenda? There you go. Next one. There you go.
Okay. Perfect. So today we have a collection of esteemed speakers from universities around the country. We have Hector Lugo from the University of Texas at El Paso. We have Michael Yang from UC San Diego, and we have Carl Whitesell from South Mountain. Next slide, please.
All right, then. I guess I'll start.
Okay.
Thank you so much,
Okay.
Glenn, for the
Sure.
introductions and for showing the order. So, hello, everyone. My name is Hector Lugo. I'm from the University of Texas at El Paso, and I collaborate with the Electrical and Computer Engineering Department. Right over here, you get to see Patricia Mendoza as well. So, go Miners. Woo! To talk a little bit about our experience with the makerspace, this is a little bit personal, and the reason being is because I actually graduated from the University of Texas at El Paso. I did my bachelor's and master's at UTEP, and what I found out to be is that on the senior project, when I was doing my senior, that's when it was really hands-on, and you had to make your own PCB, and then you had to find creative ways to actually make your final presentation, which is a whole year, when you do your research prototype and then get to showcase your final product. And one of the things that I found is that as I continued doing my senior project, I ended up seeing that there is a huge need for the makerspace, or a place where students can actually collaborate and start building projects. Just to show you some demos, this is at that time, it was barely starting the 3D printers, and we got to see flexible material. So being as a student, sometimes it's hard to be able to achieve, or even to purchase, or even to manufacture from outside, or even get to do the PCBs. We're on low budget, right? So with the fact that we were using the 3D printers within our department when I was working as a part-time student, and then they actually got to purchase a 3D printer and then use flexible material, it enhanced the whole experience on my senior project. So as you can see right over here, this is a remote control that we actually got to do in our senior project, where we got to program the MSP430, then all the push buttons and PCBs. So from that experience on our senior project, we got to see that this is something that it really helps on our side, and we were working and collaborating throughout that generation. A lot of students were asking me, hey, you have 3D printers, can you help us out print this items and these items? And then we're like, sure, we'll definitely help you out. So we see that there was a huge demand to showcase some of the things that we have done in the makerspace. As you can see, we have presented on ASEE as well, with conductive materials. So once you put the battery right over here, it would actually turn on, and then it would showcase ASEE and UTEP. This project was student-based focus. So the students that are working within our part-time are also electrical engineers as well. They start integrating more hands-on projects where the ideas are endless, you get to see a lot of things. Sometimes it helps a lot, the project-based learning projects, or sometimes being able to cover a topic so that they can be visual. So right over here, you get to see binary. So for example, for binary, sometimes it's hard to see ones and zeros, and then how it actually goes into the numeric numbers. But just by filling these options, now you actually get to see the binary, how it actually works with the zeros and the ones right over here. We use this for Techie Teach, where we actually teach K through 12 outreach. And it also helps for students, not only just on college level, but also from kinder all the way to college, or at any age. You can actually get to grasp some concepts of binary or computer science or electrical engineering. Some other things that we have done, as you can see, cybersecurity as well. Some projects right over here as well. So what I was going to show you is a video, but it was going to take more than 3 minutes. So I just put it right over here on the chat, and you're more than welcome to download or watch the video of some of the things that we have accomplished. What we do on the makerspace is heavily student focused. So we support student orgs. Sometimes they're creating virtual reality games. They're collaborating with other professors such as Elite as well. On that video, you're also going to see how students from electrical and computers have done their research, have done their senior projects, from even crafting new things to doing prototypes with equipment such as laser engravers, 3D printers, and things like that. I don't want to take too much time. I usually tend to talk too much. Are we with time?
I think you're great with time, and so I definitely would like to ask about the 3D printed binary blocks. That seems to be that's a great idea. And can you talk more about the student outreach aspects of the makerspace, and if that falls in line with the mission of the makerspace to help STEM level students understand engineering and develop an interest in that topic?
Yeah, it has created a lot of interest. What we do is some of the things that I have seen that sparks a lot is that students teach students from the same course or even from previous courses. And the way that they teach each other, they try to teach it not only just in theory, but also in a physical, in a more hands-on practical way. So the students are the ones that are actually giving us the ideas, or they actually get to craft the ideas. So for example, this one right over here, a student was, in a sense, we were teaching K through 12 students, but then when we were teaching the theory on paper and then on the projector, they were like, there needs to be a different way to be more hands-on, to be something more tangible. So that's when the students design, we talk about it, and then they come up with this idea of, you know what, let's use the 3D printers. Let's make something that it's easy, that anyone can use it, and that they can actually relate to it. I also attach on the chat. So we started tracking the makerspace within our university. And as you can see, there's like roughly 36,000 users that have actually signed in, or they're using the makerspace. And we started tracking this since December 21. So we started like on 2017, roughly. So that is only the number of students signing in. But we also have other numbers when it comes to 3D printing as well, where the students can actually 3D print anything, which is, we have found out a way where it doesn't have to be super expensive to be able to support the experience for students to be able to 3D print. It costs roughly about $6,000 to be able to support all the students' their prints. So it could be something from personal projects to course and research projects, or anything else for the community as well.
Thank you so much.
Yep, no worries.
And okay, so we are going to move on to Michael Yang from UC San Diego.
Hi, my name is Michael Yang. Yeah, I'm from UC San Diego's EC Makerspace. And I'll just be talking a little bit about our space and what we're kind of working towards in the future, and a little bit of our mission. Because the EC Makerspace was established to solve a problem, and that was that engineering students are graduating with a lot of theoretical knowledge, but maybe not too many applicable skills for the workforce. So our mission is to provide engineering students with a space to gain hands-on experience through classes, workshops, so that they're more ready for the world upon graduation. We have a wide variety of classes that have been held in Makerspace that have really changed EC education, like EC 115, our rapid prototyping course. This course teaches students to design mechatronic systems in response to a problem. They get the 3D model, rapidly prototype solution using our 3D printers, laser cutters, and electronics. And most importantly, they get to see their prototypes fail and learn to rebuild from that. Students really get a feel for how to actually make machines and electronics work, and the nuances of design that come from failure, repetition. That's really hard to convey without actually doing it themselves. I also like to think of our makerspace as a bit of a jumping point for many students into interdisciplinary fields that they're less likely to broach in traditional classes. Makers need skills, but they also need inspiration. And I believe that the best way to gain that inspiration is by bringing in challenges and expertise from other fields and having students run with that. For example, a lot of our work in our past has been to supporting our project-oriented student organizations, like Project in a Box, advised by Nick Stein. Their goal is to design project kits that fit in a box, hence the name. And the goal is easily portable and distributable project kits for outreach programs, like their monthly workshops with the San Diego Public Library. But that's a big thing. Students who are part of this organization aren't just designing for like a nebulous purpose, but with an eye towards education. In a similar vein, we also have a lot of great programs and ideas that are coming up that we're really excited about. One area that we're working on are interdisciplinary hackathons. So the goal here is to reach out to other departments outside of ECE and bring in their problems and perspectives, and have their students and our ECE students form teams to create something beyond either department. Some areas of focus will be around sustainability, activism and visual arts, cognitive science, accessibility. And I'm really hoping to introduce like ethnic studies, biology, and a lot of other schools of thought into our engineering spaces so that our students have a larger pool, I guess, of perspectives to draw from. Following this, we're actually gearing up to introduce a makerspace grant program this year. We'll be funding and mentoring independent projects and potentially projects derived from the hackathons that we're running. This would be a kind of a guided grant program where each quarter we have our groups set deadlines for themselves that we monitor, and we connect them with student and professor mentors and showcase their work at the end. There's going to be a lot of workshops along the way too, to make sure that our students learn both basics so that anybody can be joining these programs, and more applied uses of hardware in their projects. So yep, our school year is about to start, and we're really excited to see what we can help our students make.
Very exciting there, Michael. So failure, I think, is something that every student has to experience while working on an engineering project. If I've been to your space before, if I may suggest, you should have a wall of fame or wall of infamy, whatever you want to call that, but to highlight the interesting failures that led to good outcomes. Really quick about interdisciplinary use of the space. That's a great idea. Are there trainings for students from other majors who may not have necessarily the electrical or maybe even the hands-on skills to start using the equipment you have in there?
Absolutely. Well, our hackathons are generally designed as like a maybe one day or like a one weekend sort of thing at the very beginning, in which, you know, some students will bring in their perspectives, and then our ECE students will bring in their more practical like engineering knowledge that we can mesh that together. But as Hector mentioned, a lot of the times in these programs, you see students teaching students. You know, once we have project teams and things, we start having workshops. We start having, you know, students like talk about like, oh, hey, here's how I use a laser cutter. You know, come with me into this space. We'll work on this together. And honestly, this is a really good way for the campus as a whole, really, to learn a lot more maker education.
Awesome. Thank you so much. And now I'm moving on to the next person in the list, Carl Whitesell from Carl. Are you there in the audience? Oh, okay,
There.
perfect. Just have to make sure.
All right, yeah.
Okay,
I'm
I
gonna
am
bring
great.
up. I was asked to come and speak to you about what we're doing here at South Mountain Community College in South Phoenix. My one thing to know is that when I'm finished, I have to leave. I have a class that is meeting right at this moment, actually. So my lab manager is watching over them. So with that said, I was asked to talk about our lab and lessons learned. Notice I did not use the term makerspace, and I'll talk about that in just a second as to why. Okay, so the idea behind this is actually pretty simple, a little bit of history. In 2016, my administration had said, hey, we need a makerspace. There was a nonprofit organization that was willing to donate the base equipment, meaning the 3D printers, the lasers, a micro mill, vinyl cutter, electronics, the ShopBot mill, and all that. I came on board in spring 2017, and that was my #1 project, was to get this lab, get it up and running, and make it so that it's something that the whole community can use. While this is a donation, it does have to go through the upper administration, meaning the governing board, and they were against the term back in the day, makerspace. They said, no, we don't see the point of a makerspace. And so I had to kind of finagle the way through it. And so while it started off with the equipment of a makerspace, it is what we call our engineering lab. And since then, we've expanded what we're able to do beyond what some of the typical makerspaces do. 2018, it was approved. The equipment came. The building was being redeveloped, so we finally had a home for it. We had a grand opening in fall 2018. And then since then, for spring 2019 to the present day, we've had a huge success, but there are continuing issues on this. If this is something that you're interested in learning about, I worked with Skyline Community College in San Francisco as a partner on this. And we actually presented a conference paper about this at the American Society for Engineering Education in 2019. So anyway, as far as the lab goes, when it started off as a makerspace, the initial equipment that we started off with was 3D printers. We had an Epilogue laser fusion. or Epilog fusion laser. We had the ShopBot mill, we had the vinyl cutter, and then we had the Roland micro mill. So right off the bat, the problems that we had identified was that this has to be hands-on. So if you're thinking about putting this in a school or something like that, the more stuff you have, the more space you're going to need. Initially, I had one classroom, and we took over an entire 4-room building to fit all of this into. But since then, we've outgrown it. We need a constant source of funding to maintain the equipment. Initially, when this was done, it was never discussed. I would bring it up, but the administration wanted it so badly that they just said that's a problem later on. The intent was what a makerspace is, a place for students to design stuff. Okay, staffing is another issue that we've run into. The students are very eager to use this, but on their schedule. And so we need staff that's able to meet the needs of the program and the students. And there's a demand to have this done outside of school. And that's the big issue that I'm having. Finally, the equipment. The students are excited, but the base equipment didn't address everything, which meant we needed more money in order to expand what we did. So finding solutions. I became a grant writer. I wrote a lot of grants, and that's how we're able to pay for a lab manager. I run the program and I teach, and I can't run the lab at the same time, or at least fully run it. So we were able to land a grant that pays for our lab manager. We used grant funding to pay for a student work study to help us staff the lab. We've used grant funding to pay for new equipment. The other thing that we've incorporated this is student fees. We have the use of the lab, the required use of the lab, incorporated into some of our classes. And I got to say, Michael Yang, you're one of my heroes. My son graduated from UC San Diego. And what you said you did is exactly what I'm doing here at South Mountain. Multiple usage of the lab. I work with other programs here for the services, and then we just charge them for the consumables that they use. So the English program will send students over here to create something that gets etched on the laser of one of their heroes that they write about and things like that. It's available to the community. It's open to the community to use, but we do charge them for use of the equipment and the consumables. And then I am constantly begging for money. At the end of the academic year, when there's funds available, they'll announce it. And I'm the first one to jump in there and say, hey, we need it for this, and then go from there. We're able to survive, but it could be better. So that's the big lesson that was learned. As far as the equipment solutions, we have since expanded it. We have the oversized plotter, because when students are doing any sort of research or things like that, they usually have to produce a poster or things like that. So we have the ability to print posters. We expanded our 3D printers. We were able to refurbish a MakerBot, and through grants, we were able to land 8 FlashForge 3D printers as well. So we have 11 3D printers. We found digitizers. So if you don't have the file to create it, you can scan it and create it. We put into a Lincoln Electric MIG welder, so the students can learn the basics of welding in the lab. And then we have a Bernina industrial sewing machine in there as well. So for the students can, we use a badging process. The students come in, they set up an appointment, they get trained on how to do it. They show that they know how to use the equipment, they earn a badge. And when they come in later, they don't have to be retrained or anything like that. They just show their badge. The students love this. This is a coveted thing on campus. Students walk around showing each other their badges. We expanded the equipment into power tools as well. Originally, we had the bandsaw and the drill press. Actually, the bandsaw came with the lab, but then we expanded it out into the belt sander, the drill press, the table saw. Pretty much anything that you would see in a carpentry shop is what we've expanded to. And then we also have it in cordless versions, because sometimes the projects that the students work on are on the other side of campus and they can't bring the stuff here. So we have that available for our students in our lab. Staffing solutions, as I said, we used a grant to pay for the lab manager. We use it to pay for the student work study staff. I have reached out to local industry for internships for our students, and we were going crazy with that, and then COVID hit. We're revamping that, and we've started to get students landing internships. However, there are also scholarships that require that students participate in internships, and so we actually sponsor their projects in the engineering lab if they come in and spend their time working on those projects in the engineering lab. Same thing for honors students, we incorporate that for them as well. We try to keep it open as many hours as possible. It went from me running it to just a couple hours a week, because that's all I could fit into my schedule, to we are open Monday through Friday from 9 to 5. But as I said, there is a demand for it to be open on the weekends, preferably Saturdays, and in the evenings, at least until 8 o'clock. And that's the part that we're still trying to fix and trying to raise. So with that said, I thank you for your time.
Thank you very much, Carl. And you brought up a very interesting aspect of running a makerspace, and that is staffing and time.
Mm.
That's something that a lot of people do not think of. They think, well, let's create a space.
Mhm.
And if the doors are not open, the space is not used. And so I really appreciate your insights on when students prefer to use the space. And yes, it should be available as often as possible. Then you've become a facility.
Yes.
Then you have to worry about running a facility there as well. So I really appreciate your
having
insights on
our
that
lab,
one.
our program has expanded. When I started here, we had 32 students. We now have 252 students. And word has gotten out. There's none other in our district that has a makerspace lab like we do.
Perfect. Beautiful.
Thank you. Now I got to go see my students. Oh, I don't know. Is there any
Absolutely.
questions or?
Are there any questions for Carl, for Mike, or for Hector? Let's see. Sean has a comment here. For anyone talking about their school's makerspace or lab, or have experience running a makerspace or lab, how do you encourage students to make use of the space? In my experience, I see many schools create such a space, offer access, only have the tools collect dust.
I can speak a little bit on that, actually. So one of our student staff that we're very focused on trying to acquire is a communication student. We try to make a newsletter and try to reach out through our different department newsletters and all that, try to encourage students to come through more often and like check us out. We also try to host a lot of programs that would encourage students to come look at our spaces as well.
So one of the things that we do for getting other students involved and make sure that they're using it is incorporated into 2 courses that we offer. Those courses actually meet in the makerspace, in the lab. So it's not like a classroom and they have to come to us, and they are required to use it. In another course, students can earn extra credit for going through the badging process as a way to encourage them to use the lab. And then we don't do like a newsletter, but I actively reach out to the other faculty. The English program loves sending their students over here. And we get a lot of students from the art programs who like to come over here. And then word has just gotten out that this is something that's available for the students. By the way, the engineering students don't pay a fee for this. It's part of, we take a small little bit off of their lab fees for it. The non-engineering students, they just pay for the consumables. And then the community, we charge them for use of the machines and the consumables.
On our side, what we have seen is that the engagement between students, they start talking to each other, they spread out the words or the makerspace topics and how the whole community is helping each other. Our makerspace, it has full-time staff, but also our part-time students are the ones that are also helping from 8 a.m. all the way to 10 p.m. And it's all about the support and making them feel like it's a safe place where they can actually just talk to each other, help each other, support each other. That if they're trying something and if it doesn't work, that they can try it again, and that they can actually, there's also people that can support them, help them out. some of our students that are from STEM, electrical, computer science, mechanical, but also we do hire people that are outside of the STEM field as well. So it's all about a mix. And then the fact that there is a place where they just hang, it gets super busy on our side. So it's really nice to see that even after 5 p.m., students are right over there while they're just giving a workshop about something else as a student organization. There's also students working right over there working on their projects. So
yeah, Hector, one of the things that you mentioned is something that we actively do. We encourage the students who have been badged on the equipment to train the other students. The students are much more interactive with their peers than they are with me or our lab manager. And so we try to ask the other students, hey, would you be willing to teach somebody how to do this? And that seems to be going really well.
Right. Well, I think we should move on to the next segment, if that's okay with you.
Absolutely.
you.
So
I gotta
Carl,
go to
Hector, and Mike, thank you so much. Carl, go back to your students, please. They're waiting for you. Okay. Okay, so initially I wanted to share my screen to introduce the next person, but Kevin, are you in the crowd? You know what? Instead of showing them a slide with a picture of you, you're here. Why don't you hop onto the screen? So Kevin is our in-house maker at DigiKey, and you've probably met him at prior ECEDHAs before. As you can see, that's what he has in the background. He's Mr. Maker. So Kevin, go ahead and introduce yourself, and let's talk about the Makerspace Startup Guide.
Well, thanks for the introduction. I'm assuming you can hear me. Zoom and my computer don't work well together, so it's working, so it's a good day.
We can hear you.
Perfect. So thanks for the introduction, YC. As YC said, my name is Kevin Walseth, and I work at DigiKey. I'm not going to go into this huge introduction because I'm going to talk about the Makerspace Guide. But, you know, my team, we do work on everything Maker related, Maker Faire events, Maker.io website. Maker is kind of where we live and where we breathe. A lot of new products, you know, anytime there's a new board or a new thing coming out, that's kind of what we live and breathe. Also 3D printing, starting to do a little more laser cutting. So I'm going to see if I can share my screen here. Yeah, let's see. All right. All right, so this is the DigiKey Makerspace Guide that we created a few years ago, really to build makerspaces across the country, whether it's a university, whether it's somebody's basement, a business wanted to put a makerspace in, you know, a closet back in the corner or down in the basement or whatever it is. You know, makerspaces have been on a huge rise and there's a lot of excitement around it. And the barrier to entry for creating any product or project or just having fun is so minimal these days with Arduino boards, Raspberry Pi boards, companies like Adafruit and SparkFun. They make everything just so easy. So we put this guide together, you know, just to kind of give a starting point for somebody that may want to create a makerspace. So like I said, what this guide does is it kind of gives you an overview of 3 different sizes of makerspaces. We call them micro, standard, and mega, just to kind of fit in with the, you know, the cool naming nomenclature of technology. And, you know, this can start from everything from furniture to what kind of tools do you need, what areas is your company or your university looking for to create makerspaces. You know, there's also different considerations like environmental considerations. You know, what do you need to do to stay green in your makerspace? What about Wi-Fi? You know, there's also the costing structure. I mean, I know cost is a big issue, and you know, the last presenter you talked a lot about costs and ongoing costs, and you know, it kind of made me think, you know, maybe I should add a little more to this because there's a lot of things to consider, and that's the ongoing cost for keeping the equipment up and running, for the consumables, and you know, different things like that. So you know, this is an area of the guide that just really talks about what are you looking for when you're planning a makerspace. You know, what do you need for furniture? How many people are you going to have in there? Are you looking for basically a machine shop, or are you looking for an electronics makerspace? What about prototyping? 3D printers, laser cutters. Those are probably the biggest things that people think of when they think of maker spaces. At least people like me that love making, that's what I think of. And then how about the electronic side? Are you going to be doing soldering and desoldering and reflow work? Do you need a pick and place machine? What kind of level are you working at? And it kind of depends on what your classes teach and what kind of projects your students are working on. You also think of CNC machines. There's a lot of things you can do with a CNC. So there's just so many things to consider. And reading through this, my goal with this is, as you read through this, it'll give you some ideas and turn light bulbs on and be like, I think that would work in our makerspace. That would work with this class or this class, or with these students and this senior project. This just goes on a little more in depth to it. It kind of keeps going on with CNC machines, and then the wood shop. A huge makerspace would definitely have a wood shop and everything you need to build basically custom cabinetry. But you may not be building custom cabinetry, but you may be building enclosures for who knows what. So wood shop is pretty necessary. Everything from a table saw to band saws and skill saws and drills, and how do you glue everything together? And when you think of a wood shop, you're also going to need sawdust contraptions, so you can take all the sawdust out of the air and keep the air clean. And how do you dispose of that? And also a machine shop. I personally would love to have a machine shop. That's something that if I was able to build a big makerspace on DigiKey campus, that's one of the first things I would want, is a machine shop, because that's where you can really get custom and build some really high-end next generation prototypes and designs. And it's going to take a lot of space, it's going to take a lot of money and a lot of training. Laser cutting is something that most maker spaces will have. Laser cutter can also be a laser engraver. Are you going to cut out signs and create 3D replicas of whether it's a picture of your state or a project? I know he mentioned in English class creating their hero. You can take a laser cutter and basically create your hero out of wood in kind of a 3D type of a topography. It's pretty neat. So laser cutters are also a huge part of this guide. Welding is another one where if you're going to have a makerspace and you're going to be prototyping, you're going to need some welding equipment and some training on it. And then are you looking at a MIG welder? Are you looking at different kinds of arc welding, or whatever it might be? But then you got to think about the safety gear. You have to do training on using the helmet. Definitely don't look at a weld live. We all know that that's a bad thing, but do students, is the question. So training for everything is something that is very important. Electronics, now that's where DigiKey specializes. We have electronics, we know electronics, and that's the area where we can help a lot in maker spaces. And you talk about rapid prototyping, and you talk about soldering and desoldering and building a circuit board. I mean, you can even build circuit boards on your own in-house with etching, etching your own circuit board. Or there's the Bantam Tools CNC mill that you can create a circuit board on your own with a CNC machine. And then learning how to solder, learning what the wire traces sizes may need to be. I'm hoping most people on this call have one of the DigiKey rulers, and this is great for PCB layout. That's something that we hold near and dear to our heart. That's one of our favorite giveaways for all events, but it's also very useful. So, also a lot of engineering classes, they're going to teach you about resistors, capacitors, and you can do different tests inside of a makerspace electronics area. What happens when you, or how do you blow up a capacitor? It'd be kind of interesting to do that with kids. The only reason I say that is because my college instructor did that, and it was one of the funnest days we had in the school. So it's a lot of fun. Textiles, creating wearables is something that's really big right now. So what are some things that you may need for textiles inside of a makerspace? Sewing machines, um, embroidery machines, vinyl cutters, these kinds of things are pretty common and pretty widely used in creating and prototyping. So we definitely are going to want some textiles. Wearables, as I mentioned, you look over YouTube, and specifically when Halloween comes up, the wearables that people are creating are unbelievable, and a lot of them are done in maker spaces. So what are you going to need for wearables? Are you going to add lights to it, which brings in the electronics area? Are you going to need a sewing machine? Let's move on to the next. So then some of the environmental considerations. I mean, we all know that when you solder, you need to have a fume extractor. What other environmental factors do you need to bring in? You have to make sure your ventilation is really good for your laser cutters, for all of your machinery, like I mentioned, the sawdust from all the carpentry tools and the workshop tools. But that's something that really needs to be considered. What about eye care? Do you have an eye wash station in there? Do you have an emergency shower if you're going to work on chemicals? Those kinds of things are something to take in pretty big consideration when creating a makerspace. So when I put this together, my goal was to have 3 different sizes of makerspace, and what is kind of an example. And this is kind of a rough sketch of, if you have, up to 1,000 square feet, what can you add in here? And, you can look through this, but basically 3D printing, a small desktop laser cutter, electronics area, a soldering and assembly table. You're going to need a few computers for programming Arduino, or for programming Raspberry Pi, or whatever it might be, and also computers to run the 3D printers, the desktop laser, and the desktop CNC, and also some test and measurement equipment. If you put together a circuit board and it doesn't work, you better have some of the equipment you need to test it and do some debugging, do some measuring. And that's could even be part of a class, like what is the resistor capacitor putting out for measurements in an RC network. And then textiles, like I mentioned, textiles are so popular that you're going to want to have at least something in there, even if the smaller micro maker space is something as simple as a vinyl cutter. But that's something that everybody loves. Stickers. If they can create their own stickers and create their own logo, that'd be pretty cool. Also some digital tools. VR headsets and 3D scanners are really popular, especially the 3D scanners. If there's something you want to create, you just scan it and 3D print it. And then some basic coding products. We have different products from companies like SparkFun, Adafruit, Raspberry Pi. You can get like a Circuit Playground Express, which has all the different sensors already built into it, getting started guides, learning guides, and it's a really good introduction to electronics. And then obviously you're going to need a tool chest with hand tools and wire crimpers, wire cutters. Hot glue gun is a must in a makerspace. You probably should have one of those as well. This is just a list of kind of a quick list of some of the products that you may want in a micro makerspace. And then moving on to a standard makerspace, you're talking a classroom size, a pretty big classroom, 2,000 to 6,000 square feet. If you have quite a bit of room, these are some of the things you might want. You're going to want rolling carts to be able to move from station to station with some of the tools. The prototyping area is a pretty cool area in my mind. That's probably where I would spend a lot of time. You're talking sewing machine, fabric table, a whole screen printing area. I mean, if you could have screen printing in your makerspace, your school could create their own shirts for whether it's a homecoming game coming up or something. They could make shirts for the entire junior class, or the entire football team or volleyball team or whatever it might be. 3D printers, laser cutters, and then moving into kind of limited access tools. Now this is where some of the conversation about who can use what machinery, how are people limited from using something they're not trained on. And I know one of the conversations was you have a card and you have basically that card gives you approval. You know, I looked into creating a makerspace at one point and using a scan, like your badge, you will get access to use like the table saw, and you have to go up and you have to scan your badge at the table saw in order for it to even turn on. You know, that's something that you really need to look into when you get into some of these bigger limited access areas, like especially if you get into machine shop type of an area. You don't want anybody going and trying to use some of those machines. It can be very dangerous. And then an entire electronics area would be pretty cool. And then a classroom area. If you have a bigger makerspace, you need to have an area where you can sit people down and do a class on a weekend or do a class on an evening, or bring a class to the makerspace for a specific topic. What it could be electronics, it could be 3D printing, and have everyone sit down at the table and demo it and have it up on the projector and kind of explain what we're doing, what you're doing. So that's something you'd like to see. Another list of the tools and the textiles that you'd want. And then a mega makerspace. I mean, this is one where you're talking about an entire building. An example of this would be the University of Wisconsin-Madison makerspace that we were at one point. And it was a beautiful facility and there was so much room in there. Now, this is where you can really get into the cool things. Like, I have listed on here a water jet, a CNC mill, a lathe, welding areas. You're going to have storage for some of the consumables in every different area, whether it's the woodworking area or the metal shop area. Again, you're going to want a classroom area, similar prototyping and woodworking areas in this size of a makerspace. And one thing I don't have on this is you're going to need more storage. You're going to have to be able to have an area where you can have storage. And I'd also like to see an area where you can rent out tools, like the hand tools. Like if you need a drill for an afternoon for a project, you can go up and you can check it out. So you can make sure it's not stolen. There's accountability factor on it. So that's what we're thinking for a mega makerspace. And again, this is just a quick listing of some of the bigger machinery and products that you would want in a large makerspace, a mega makerspace. And then at the end of the guide, we just have some, grid paper that you can design on. You can design your next cool prototype or your next cool project. So that's what I have for you guys today. I hope this was informative. I hope this is good. We'll send these out to the next ECEDHA, some of these guides out to the next ECEDHA event, so YC can hand them out. And please let me know if you have any questions.
Kevin, I'm getting emails from people asking for an electronic copy of the guide. So if you can email me a copy, I'll be more than happy to forward it on to the attendees of this meeting. But
yeah, I sure can.
Okay. Kevin, thank you so much for your time.
You're very welcome. Thanks for having me. It was great to see everybody, and I'll stick around and listen for a little bit because this is really interesting to me. So
okay,
if everyone's okay with that.
Absolutely. Okay, perfect. So now we've talked about the formation of a makerspace, some of the challenges that lab managers run into, and also what it takes to set up your own makerspace on site. Now let's talk a little bit about the application of a space. In this case, what is being taught in one. And so Microchip, so Dave Polonian from Microchip and Ross Secho are going to present on the concept of a, I would say, an inverted pyramid top-down style microcontroller-based curriculum that will leverage the equipment in such a space. So without further hesitation, Dave, please take the stage.
Hello, everyone. I'm Dave Polonian from Microchip. I run the academic programs. And what we were asked to do is to go through the thought process that we are currently going through to determine the best approach for a curriculum that's developed or inspired by the maker ethic, if you will. I'll be presenting with a colleague of mine, Ross Satchel, who will join the discussion shortly. He's an applications engineer, and also he's uniquely gone through the transition from being a maker to being a real engineer. And so his perspective is very interesting, and you'll I think get a kick out of it. So we'll go ahead and get started. You can bring up the slides. So the again, what we're trying to do is figure out or let you know what our motivation was in pursuing this project in the first place, and to let you know in the middle of the process kind of all of the divergent thinking that we've done. Hopefully towards the end, we'll get some audience feedback from you as to where you think this approach might fit into your curriculum, and what specific aspects of adoption would make the most sense. Our hope is that based on your feedback, we'll be able to go back to the management team here at Microchip and fund the development of some curriculum that we can share broadly. So in this session, we're going to go through, what started the project, what was the motivation. Ross will cover what subjects are likely to be included in an introductory course that's based on this maker approach, and also go through the hardware and software aspects and options that you have in implementing the lab activities. Towards the end, then I'll come back and talk about some example curriculum integration. So how you would take some of the ideas that Ross goes over and plug them into various places in your engineering curricula. And then again, one of the most important aspects is towards the end, we'll actually allocate some time for some audience discussion and get some feedback on what we've talked about. So we're looking to find out more, which MCU architectures work best at what points in your curriculum, what approach to fabrication and assembly, or what approach to software development are most comfortable to or would work best at different stages. So more about the integration in the curriculum. So before Ross gets started, I just wanted to go through, what we're meaning by the maker ethic. So the traditional approach has been, we go through a bunch of individual discussions of a microcontroller, individual subsystems, talk about some of the foundational stuff, and then we also go through each subsystem, show how it's used. The pros of that are, it's been a lot, it's been the approach we've used for a long time. It comprehensively covers what an MCU is and how it operates. It's pretty well defined in terms of what you need to measure and what kind of outcomes you need in your class. And it's also, again, straightforward from a testing perspective. The cons are the students tend to, if you spend too much time from a theoretical point of view or on the minute details of a particular subsystem, keeping the students' attention. Also, a lot of the activities are more contrived. So rather than having a real world problem, you're looking at an individual subsystem and trying to get it to function without necessarily understanding its place in an overall system. Again, since these are independent activities, a lot of times there's really no tangible end system. You've just done a bunch of lab activities to help you understand the microcontroller. Very limited creativity, since again, you want to be able to measure it and you want to make it something that is compartmentalized. And so the problem solving is often focused on the math for a particular subsystem or the details of getting a particular subsystem to work. So the difference with the maker approach, which again, what we'll kind of elaborate on quite a bit in this presentation, is that your perspective changes. So you're going to create some context by having an end goal, by having a product that is going to be the outcome of all of this subsystem development that you do. So it tends to be more engaging. They're trying to get, in the case that we're looking at, the ability to have a self-balancing robot at the end, but it could be anything that's a tangible product, if you will. And so they have a more visible, tangible goal. And then because of that, as they're developing the system, they have to do a lot more system thinking and problem solving that runs the design trade-offs in the overall system. So I think you get a better system approach. In the more traditional mode, you might have a separate course later that helps focus more on the integration. But in this case, if you're combining the two, that tends to create a more acceptable, or more, it creates more enthusiasm in students. It's again less rigorous from a con side. You may not cover everything about every subsystem, but you're covering enough to get the end product working. The outcomes may be less specific, depending on how much flexibility you give them in the functioning of the final system. The testing may be more subjective, because if you're asking them to write code or cobble together code, you're not sure what you're going to get, so there won't be as clear of an outcome. Students may use some creative ways to get things done. And again, it's not traditional, so try to get it integrated may take a little effort to convince the folks in charge of the curriculum to adopt it. So interestingly enough, the cons from the traditional approach are addressed by the maker approach, and the cons for the maker approach are addressed by the pros of the traditional approach. So that's a kind of a complicated way of saying there's going to be some trade-offs, and you may have to adopt aspects of both of them in order to achieve all your goals. So what differentiates the maker ethic? Again, it's project oriented. It often involves a lot of improvements to existing software, existing solutions, rather than designing from scratch. It also it tends to be more of a rapid prototyping activity than a rigorous design activity. A lot of times the implementations are non-optimal, since the goal is to get something to work. It puts a lot more emphasis on the integration than the compartmental approach. And the other thing that is a lot of times missing when people criticize the maker approach is that once you go through all of this kind of soft, fuzzy way of solving the problem, the next step is to now look at your prototype and to more rigorously redesign it. And now you're actually starting to do the real engineering. And so the maker aspect of getting something functional can be followed up with something a little more traditional to get a more acceptable final design. So with no further ado, I'd like to introduce Ross, and he'll go over his journey getting into the engineering world through the maker pathway, and talk a little bit about what we have in mind. So go ahead, Ross.
So first, hi everybody. So who am I? So I had some electronics experience in the 1990s, but I eventually found a home in specialty coffee where I really got my geek on. And was playing with coffee. So during this time, I also started repairing commercial espresso equipment, and then customers would bring me their prosumer equipment, and I started repairing that as well. So I had a little sideline doing that. And while I was doing this, I ended up buying 2 non-working espresso machines that were shipped to my tiny New York City apartment in a pallet, or on a pallet, and I started rebuilding those. And I ended up adding off-the-shelf controls, which was happening in the industry at the time, and I'll go into more about that. There we go. So the initial problem is a lot of these machines have mechanical thermostats, while they're inexpensive, they have a very large hysteresis. And so it requires the user to learn to do what's known as temperature surfing. And so the initial solution in the industry was a off-the-shelf PID controller, and these were quite expensive. And when you coupled them with a thermocouple probe and then all the swage lock fittings that are needed to get the probe into the boiler, you're looking at more than $200. And for somebody who's doing this just as a fun project, this is getting quite expensive. So one of my coffee customers at the time, I was talking to him about it, and he said, have you heard of this thing called Arduino? It's just come out the last few years ago. And this was in 2009. And so I started playing around with it. I hadn't programmed in 15 years. My electronics experience was out of date, and I knew nothing about controls. But I leveraged existing Arduino libraries. I built this proof of concept here in the image. And I cobbled together a $10 Arduino clone, a thermocouple breakout board from Adafruit. And I even had a little homemade keyboard there. There's those 4 black dots in a diamond there, so I could traverse the menu system. And I made 2 prototypes and sent it to 2 friends who had little prosumer machines to test on for about 3 to 4 months. And with the feedback that they gave me, I then went back and developed a schematic and breadboarded everything out in parallel. And eventually I created a PCB from that. And at the time I used an off-the-shelf solid-state relay, because I wasn't comfortable with rolling my own solid-state relays at that time. And this actually included auto-tune as well, which is something that was only available on commercially available PID controllers. And that was, the auto-tune was actually done through the Arduino processing front end. And I ended up selling this through Jameco Electronics for about 8 years. They were running a thing called Club Jameco, where someone like me could come along, pitch an idea to them. If they accepted the idea, then you would go off and build everything and write up the detailed tutorial and all the rest of it. And then they would sell your kit, and you would get, a very small amount of the sales, but it wasn't, I knew I was never going to get rich from it, but it was more about getting some projects out there. And I ended up with 3 projects being sold on their website for a while before they shut the Club Jameco thing down. So what did I learn during this? So this greatly improved my engineering education because I learned my practical skills first, but just simple equations, playing around with experiments. And then later during the coursework, when I was doing my degree, I actually learned the theory behind it and really solidified my understanding, because as I would be doing the math or sitting in class, I would realize why my whatever it was that I had been working on didn't work the way that I wanted it to, and I understood what I needed to do to fix it. It also meant that I could go back and, it also made my class labs much easier, because compared to the students that weren't really used to interacting with hardware, I was very comfortable with breadboarding stuff. I was very comfortable with hardware debugging, and it gave me a lot of real world experience. And also I had a lot of familiarity with data sheets. So I was used to constantly using them. And during this time, I learned to code in bare metal C, originally with a PIC, and then later on with an AVR. And then I designed my own signal conditioning circuits. And they're often just like low pass filters and buffers and things like that. But when I later learned that stuff in class, I was able to figure out the shortcomings of my filters and improve them and do that kind of stuff. So then later on, because I went to ASU, I did an embedded systems class, which was CSE 325, and I did that in 2018. And part of the class, it was broken up into 2 parts. The initial part was using 32-bit Freescale Freedom board, where we did some bare metal work. And the second part was doing an autonomous vehicle. And the class approach for that was project-based learning. And with the vehicle, we were using Arduino due to time constraints. And so we had to work with multiple systems. So motor drive, PWM, servo for steering. And then we had inertial measurement unit for our compass direction, as well as measuring things like our velocity and acceleration, and learning things like the accumulation of error over time with an IMU, which was a really valuable lesson. And then later on doing GPS and LiDAR as well. And the experience that I had as a maker made this class so much easier. And I got a lot out of it. I ended up getting an A+. So one thing I really found in the university level embedded systems classes is a lot of students really found this field intimidating. And firstly, extensive data sheets. So the Freescale Freedom Board that we first used in the first part of that embedded systems class had a 1,200-page data sheet. And a lot of students were thinking that they had to know the entire thing, and they didn't realize that they only needed to know certain sections, but you don't know what you need to know until you actually know it. So it's one of those catch-22 situations. And also because of this field, there's a broad knowledge base required because we have to straddle the intersection of hardware, software, and firmware and know enough about each of them to be a little, not dangerous, but a little less dangerous than we might have been initially. And in engineering, we have big problems with dropout rates. It oscillates between 40 and 50%. And the contributing factors can be socioeconomic, it can be lack of support from teaching staff, it can be the teaching methodology, and all of these can couple together or work together to have low quality educational outcomes for students. So how do we improve student success in this area? And also how do we encourage students to actually pursue this career in this field? So first we need high quality instruction, and we need to use modern microcontrollers and tools. And I've had some classes where I've been using a 20-year-old microcontroller. And so it's not really representative of the peripherals that are available today and of all of the tools that are available today for that. And a lot of engineering graduates are not sufficiently prepared for the real world industrial environment. And so when I first started studying, I actually started studying through an Australian university while I was living in California, and they had adopted project-based learning. And so a lot of the feedback they had got from industry before that was that the students that you were sending us, or the graduates that you're sending us, they're good with their math, they're good with their calculus, they can do all this stuff. They cannot apply it to real world situations. And the other thing was they had difficulty working in teams. And so by doing the project-based learning and the problem-based learning, it really helps cement this, applying this knowledge to real-world environments. And often the students have light bulbs going off all the time in their heads. And so around the world, regions that have embraced project-based learning and also problem-based learning have found that they're getting a remarkable level of success when they pair them with lectures, which is exactly what Dave was talking about before, where the pros of each, the maker side and also the more traditional side, both address the cons. The cons of each side address the pros of the other side. So they really need to be coupled together. And the idea here is that the lab or project takes place throughout the entire course, rather than you learn the theory and at the end you do the labs. So they requested some student survey feedback on project-based learning. And it was a small group, there was only 41 students. But the questions were, the first one was that the project reinforced the concepts that they learned in class. The second was that the project raised their interest in electrical engineering. The third was the project raised their interest in embedded systems. Question 4 was that having real engineering problems made the project more interesting. 5 was the project raised their teamwork capabilities. And 6, that the project was worth their time and effort. And so, yeah, as I mentioned, the sample size is quite small, 41, but we're going to dive more into the descriptive statistics here. And so they found for all questions, so the responses were 1, strongly disagree, to 5, strongly agree. And for basically all of the questions, the answers range from 3 to 5, from neutral to strongly agree, except for question 5, where one student rated for 2. And question 5 was the teamwork skills, which is, teamwork is always an issue in academia, and that's a whole can of worms on its own. So the standard deviation of all of the questions were almost in the same flow, except for question 5, as we noted above. But the results indicate overwhelmingly positive student views towards project-based learning. And I have more details of the statistics in the appendix. So our proposal is an academic kit, and it would cover hardware, firmware, and software. And it's an incremental hands-on lab that will eventually culminate in a self-balancing two-wheel robot. But before we dive into that, we needed to define some things. So first, what is Arduino? I think most people here would be familiar with it, but it's an open source hardware and also prototyping platform with a massive user community. It's also a programming language, which is a variant of C++, which basically has additional special methods and functions that abstract away a lot of the underlying complexity from the user, for better or worse. User programs here are called sketches, but the user can also program in bare metal C or even C++. So also, what is an Arduino shield? And so these are stackable daughter boards, and they're ideal for prototyping or getting a proof of concept off the ground, because you can just stack them together and get your basic idea working and see if it's worthwhile pursuing. We also have the Microchip Curiosity Nano development board. So these are PIC and AVR development boards for 8, 16, and 32-bit. Each board has a built-in programmer debugger, and it's equivalent to a PIC Kit 4 in-circuit debugger on the board. It also gives the user one user LED, one user button switch. Most of the I/O pins are broken out, and it'll have either a USB micro connector or a USB-C connector, and they're a breadboardable form factor. We also have MPLAB code configurator, which is MCC. And it's so we have MCC Melody, which is for 8-bit, and then Harmony, which is for 16 and 32-bit devices. And it's a graphical configuration tool for microcontroller peripherals, and it gives the user access to common system functions such as your clocks, your pins, your interrupts, all that kind of stuff. It also creates hardware initializers and also peripheral libraries that you can just use an API for. And so this API is basically an abstracted driver, and the header and source files are really easy to find. And this is one differential between this and using Arduino, because with Arduino, often finding the header and source files that things are referencing is quite difficult to find. The libraries here implement complex functionality and protocols, and it's an abstracted portable API. So you can move it from one microcontroller to another with not a lot of extra effort. We also have MPLAB X, an Arduino import tool. And so this allows low-cost debugging of Arduino projects. And you can import your Arduino project into MPLAB X, and it currently supports AVR DX and EX devices. So the DX as in the DA, DB, DD, and so on. And you can debug your Arduino project beyond doing your normal serial.print statements in Arduino, which are really annoying, to be honest. So I was working on a project on the weekend, which is an Arduino project, and I got to the point where I really needed to debug something, and I'd spent 2 hours trying to debug it in Arduino. I then imported it into MPLAB X, set some breakpoints, stepped through the code, I found the problem in 30 minutes, fixed it, it was all good. And you were able to pause, step into, step over, run to breakpoint, run to cursor, all of the usual debug options that are usually available to you. And it uses that Curiosity Nano programmer debugger that's built into the Curiosity Nano board. So if you were to compare it to Arduino 2.0, which does have a debugger in the IDE, but it requires the user to have either an Atmel ICE, which are $150 plus, or a Sega J-Link, they're $500 plus, or some other open OCD debugger, and they're around $500 at the moment with the supply chain constraints. So we need to make some design decisions, and we need to choose the best options. And we have 4 hardware options, and we need your help to down select to 1. We also have 3 software approaches, and we need your feedback on which are most suitable for your classes. And it may be that multiple are most suitable for your classes if you're teaching multiple different year levels. So our academic kit proposal. So the hardware options are, and we'll dive more deeply into each one, but the first one is a custom Arduino shield for the Curiosity Nano development board. Another one is using Quick or Stemma, which is an I2C bus, available from Microchip and SparkFun, or a Micro E-Click. And the another option is just breadboarding everything. And the software options are using Arduino for beginner level, the code configurator, MCC, or a Melody for intermediate, or bare metal C for advanced users. So in terms of the software approach to things, so there's some commonalities between the Arduino and MCC approaches, but at the end of each module that the students complete, what we're suggesting is that the students would complete small assignments involved around a scavenger hunt, and they would go through and look at the underlying library code and then complete small assignments And so the idea is that they would report back what peripherals were being used, what register and register settings were being used by either Arduino or MCC. And then the student can also then try to figure out what they think would happen if a particular register setting was changed, or if the configuration of a peripheral was if the peripheral was configured differently.
Just had a quick comment. One of the approaches, or one of the arguments against Arduino is that when students use the Arduino development environment, they're very highly abstracted space. They never really see the microcontroller. So what Ross is proposing here is that in order to mitigate that a little bit, you get them to get the project functioning using the Arduino abstraction, but then you give them a peek, or force them to take a peek under the hood to actually see what was involved on the microcontroller in order to get that thing to function. So it's a way to get kind of best of both worlds. The student gets quickly to successful functioning, so they get a motivation to stay involved. But then before they move on, you require them to take a look at what it really took to get that thing working. And what we suspect will happen is it gives them a greater appreciation for a more traditional top-down top-down approach to designing individual subsystems in a more traditional way.
So yeah, as Dave was saying, get the students comfortable with using the data sheet and also the header and source files, so they can see that at the end of the day, really, if you have the data sheet, your header and source files open, you can pretty much do everything that you need to do. But we need to smoothen or lessen the learning curve, or make it a little less steep for students to make it more approachable. So the first academic kit proposal software side is the Arduino one. So students would leverage the existing Arduino libraries, and some would be official ones, say from Adafruit or SparkFun, and some might be community-based, where the student actually go and find somebody's library, some random person on GitHub. And so this is ideal for freshman students and introduction to engineering classes, because it's highly abstracted and it gives the students some easy wins on the board, and hopefully ignites that passion for engineering. And this is a really good time to introduce test-driven development, or TDD, and get them thinking about that before they start taking other software-based classes, because then they can take this with them throughout that. And so we have a little code snippet here, and it's reading an analog pin on an Arduino, and it's a very simple analog read. And anyone who's done Arduino has done this before. We're going to basically reference the same thing in different ways for the different software proposals. So the second one is doing MCC, and so that's at an intermediate level for perhaps junior students. And so it's a GUI, or graphic user interface, to configure the microcontroller peripherals. And the students will need to study the data sheet in parallel and see how they need to set something up. But rather than being right at the register level, they can use a GUI to set that up. And so it makes that getting closer to the hardware a little more approachable and a little less intimidating. And so it eases that learning curve. And again, they can use test-driven development, and we'll talk more about that later. But we have the MCC equivalent, and this is code that is generated by the MCC GUI of getting a single ADC read. So then you can actually see the underlying code as it sets the channel. It disables continuous conversion, starts a conversion, waits for that to be done, and then returns the result. So the third one is working with bare metal. And so the user or the student would work with the microcontroller datasheet, the header file, and any relevant tech briefs. And also, if they're using breakout boards, they would need to have the device datasheet for that open as well. And they can develop bare metal C drivers for, one, the microcontroller peripherals that they're using, two, any external devices such as breakout boards or LCD displays or anything like that. And three, they need to really, it makes them think about how they need to restrict access to the hardware drivers and providing their software with an abstracted access to the hardware, but at the same time, they have to design their software well so they avoid excessive overhead because we have very limited resources in microcontrollers. And again, a normal test-driven development approaches can be used. And so then again, I have a bit of a code snippet of a bare metal C driver that I wrote for an AVR, and some of the functions that are available for that, for example, start and stop conversion, waiting for the conversion to be done, etc. So the hardware options, so it's kind of multiple choice, and we're seeking your feedback here as to which you think would be more suitable for your students. And so we have these 4 options. Option number 1 is us creating an adapter shield for the Curiosity Nano development board. And so it would be in the Arduino Shield form factor, so you can just stack the shields as needed. It makes it really easy to interface with Curiosity Nano using all of your existing Arduino shields. And it also enables customizable wiring options. So with these sets of headers here, you can actually route signals from the Curiosity Nano to particular pins on the Arduino shield. Because if you've ever stacked Arduino shields before, you often run into problems pretty quickly finding that a signal is on a particular pin, but some other thing is also trying to use that pin, and then you have issues. But this gets around that by allowing students to actually route those signals individually. The second one is using the Quick or Stemmer, which is Adafruit and SparkFun I2C bus. These are really easy to use. You just daisy chain the devices and start writing your code. So it's limited to I2C buses only. So students aren't going to learn to use those other peripherals. And there are known to be some bus capacitance issues as it gets quite long. And also students don't learn anything about wiring. They're just clicking things together and not really having to think about what's actually going on underneath. Option 3 is the micro click board with the Curiosity Nano baseboard. These are really simple to use. But it's limited to the micro click boards only. And again, students don't learn wiring here because it's all hardwired. And then option 4 is purely breadboarded, which is infinitely customizable. But the problem is when students put this in their book bag, even if it's in a box or something like that to protect it, breadboard wires come undone all the time. And then you have to spend a considerable amount of time doing hardware debugging to figure out why your project worked when you put it in your bag and now it doesn't work. And it's usually right before you have to hand it in for an assignment or show it to a TA. So we have a proposed curriculum outline. And so we're open to all and any ideas about this at this point. So to start off with, students will be setting up their IDE and learning a bit about test-driven development, and we'll talk a bit more about that in a moment. Then they would set up their pulse width modulation or PWM for driving their motors. And so it'd be things like ramping up to speed and ramping down to speed so it's not really jerky. And also learning about button debouncing, and they can use that purely in hardware doing peripherals. Then they can learn things like SPI, a serial peripheral interface, to interface with the LCD display, and then I2C with some of the sensors like the inertial measurement unit or IMU and a color sensor. Then they can spend some time with the line sensor where they work with the analog to digital converter or ADC, and also play around with the integrated op-amps to do some signal conditioning, and even the comparative to do battery monitoring. And then once they get to the motor driving, and they start working with H-bridges and learn about not having the H-bridge all sides open at once and shorting from power to ground, as well as working with interrupts and real-time responses, and also balancing the bot with using their PID algorithm. And then finally, navigating some short course where they would follow a line until a certain color is seen, and then the bot would stop. And this would be the student's application code. So I mentioned test-driven development. So it's been a feature of Agile methodology for quite some time, and it's now starting to become an industry standard in embedded. And the idea is you write the tests first before you even write any code, because you need to know what it is that you need to pass. And then you write some code to fail the test, and then you write the minimum code that will actually pass the test, and you go back and you refactor your code and tidy it up so that the behavior is the same, but it may not be quite as messy as it was initially. And you can go around and around in that circle as you, each time you add a new subsection to the project, you need to then test that, and then you need to test the whole project together to make sure that you haven't broken anything. And so if you're doing that in Arduino, there are several Arduino unit testing libraries that are available. So there's A unit, Arduino unit, and also PTW unit, Arduino assert. So students can pick and choose, or faculty can choose which one they're going to use. If using MCC Melody, Unity, which is a free open source tool, can be used in MPLAB-X, and you're essentially, part of it is you using asserts. So I played around recently and wrote a calculator, and so I would assert that 2 + 3 = 7, which of course is not true. So you get the test to fail, and then write code that will pass the test and go from there. And so there's a lot of academic papers about the approach of project and problem-based learning and the benefits to students, and educational outcomes, and also graduation rates. I strongly suggest that you do some more reading on it, but we have some links that we can share as well if people are interested. I'll hand it back over to Dave.
Dave, unmute yourself.
Okay, can everyone see this?
Yeah, we can hear you now.
Okay.
Yeah.
So let's take a quick breath. That all went by pretty fast. As I mentioned at the outset, we've been in this divergent thinking mode for quite a while, and what we want to do now is do a little bit more convergent thinking. So you've seen a lot of options about the different hardware and software approaches. Talk a little bit how they might be used, and our objective right now is to kind of see how these might fit into a curriculum. So, so what I've done here is I've taken what Ross has gone over and kind of plugged them in to what might be an approach to the curriculum. And what we'd like to do is get some feedback from the group about how it might fit. But before I go over what we were thinking, I'd like to open the floor for some questions about what you guys think about what was presented, and if there are any things that really gave you an aha, where you see a solution to a problem you might be facing, or some showstoppers, which basically say, you know, we could never get this plugged into our curriculum. So if anybody has any questions or comments right now before we go over this, we can go ahead and do that. Not seeing any hands going up. Okay, so we will go back to the share. Any of the moderators see any hands going up? I don't see any. Okay.
Not yet.
So let's go back over this. So there's four main places where we might be able to plug this in based on what we're trying to achieve. So if we're looking for a course that is going to help with retention, we can develop a kind of a overview to engineering. A lot of schools have this in their freshman year, where what you're trying to do is expose them more to the general engineering process and give them kind of a high probability of success in getting something functioning. And so again, the objective for a course like this is really to create enthusiasm and to assure that the students have something that's fairly achievable in order to reinforce the decision to go into engineering. And so in order to achieve that, based on the options that we presented, you could use the Arduino approach pretty exclusively. So that hides all the underlying hardware. You teach them things like how to turn an output on and off, how to measure something from an input, using high-level statements like that. And then also, if you provide them things that they can plug in either through the Arduino shields or some other pluggable mechanism, so they're not having to do a lot of direct point-to-point wiring. They can get the hardware assembled quickly. They're writing software at a highly abstractable level using the Arduino IDE and whatever available libraries there are for the peripherals that you have available. And so now what we have is a semester-long project which walks them through the overall system development process without making them really do any of the underlying complexities. And the students have a pretty high degree of success in getting the final project working. So that would be a freshman type thing. It might even be open to more than just the electrical and computer engineering students. It might be something that you can use more broadly for mechatronics or other courses that might need some exposure to microcontrollers. The second course is more of a foundational course. So the intent here is to make sure they understand the concepts of a microcontroller and its peripheral subsystems, and to introduce them to the need for integrating all of those. So it may not be as comprehensive as a more traditional deep dive into microcontrollers, but what you want them to do is come out of it understanding all of the different pieces, maybe the total capabilities that microcontrollers these days have, and then also how those things could be fit together. And again, since we're using a maker approach, it'll culminate in the same robot at the end of the course. The hardware, you can use either prefabricated boards like the Clicks or the I2C. You want to make it easy to extend the I/O and get them functioning. So the focus is not so much on the point-to-point connections within the MCUs, but you do want to expose them to all the different peripherals. You can still probably use the Arduino IDE. Again, they're writing in that Sketch language, which is an abstracted version of C. But here's where you might give them more of those peeks under the hood. So Ross had mentioned earlier a scavenger hunt. You can ask them, in Arduino, you basically say something like, turn output pin 1 on. And that's all they have to do in their sketch. But under the hood, there's going to be some general purpose I/O pin on the microcontroller that had to be configured and had to be turned into an output and then had to be set to the on position. So you give them some sort of an afterthought activity that forces them to take a look under the hood, maybe reference a data sheet, and get a more clear idea of or eliminate the magical kind of aspects of the Arduino. The fact that I really don't know how it works, but this is all I did. So this gets them a little bit more sensitive to the fact that there is something beyond Arduino. Real world engineering is probably going to be a little more complex. The Arduino might be still useful for rapid prototyping, but you're going to have to go beyond that if you want to get a real engineering job. So again, this is still freshman sophomore type class, and it's intended not to give them a comprehensive view of microcontrollers, but maybe more of a foundational group for embedded systems. Then the next two are a little bit more aligned with some traditional approaches. So an introduction to microcontrollers and maybe an advanced introduction to microcontrollers or embedded systems. So these two, you know, may be the same course, or they might be broken out into separate courses depending on how your curriculum is organized. If you have a single microcontroller course that's going to cover microcontrollers comprehensively, then you want to make sure that they're able to get all of the detailed skills about getting the thing set up and getting the thing operating, including using debugging techniques in order to get software running that is not necessarily working. So for the first two, the debugging is not as complex or critical. You can probably use printf statements in your C code or in your Arduino code in order to get things working. When we're in more comprehensive view and they're trying to get individual subsystems operating down at the microcontroller level, you'll need breakpoints and the ability to peek into registers and all of that. You can still probably use a prefab board, but what you'd like to do is now get them to understand the pins on the microcontroller. So some way of doing point-to-point wiring, whether that's through a breadboard or a custom board that has headers that allows you to do the wiring. And here you're actually getting down to the microcontroller. So the Arduino IDE goes away, and the my MPLAB X or a similar IDE comes into play. You'll be using Embedded C to do most of the software development. One of the things that we tend to see arguments on is whether the students should use the graphical code configurator, MCC, that Ross had referred to, or whether we should have them write the code directly. Well, there's a couple of aspects of that. So there's, one is folks don't want to get too abstracted from the MCU. When you use a tool like MCC, you're still seeing pretty much all of the different options for all of the different peripherals on the part. And you're having to decide, which pins, for example, a particular peripheral goes to. But rather than doing that through binary strings that get saved to a register, it gets done through pull down menus and checkboxes and radio buttons on a graphical user interface. Now, this all eventually gets turned into code that turns on and off bits and everything else. And the code that's generated by MCC is actually very well documented, very well structured. So you can still go into the C code and see exactly which registers are being involved, which bit patterns were placed in those registers. It's done symbolically, but it's still basically at that register level. And it's well structured so that the students actually also get kind of an introduction to structured programming. The other thing that the MCC does is it gives you these API libraries that Ross had referred to. So, for example, if you're configuring a asynchronous UART, something that's going to talk to a terminal, the libraries are there not only to initialize the UART based on the baud rates and the bit patterns that you require, but in addition to the initialization code, there's also libraries that will output a byte, input a byte, so forth. And again, they're written for you. They're in C source code. They're very well documented. And now again, the students, if you're trying to get them to a system level type of outcome, it doesn't get them bogged down in the details as much. You can still, again, depending on what your intended outcome is, force them to write some direct C, or even in some cases assembly language, to get them closer to the MCU. But you don't necessarily have to do that for every subsystem and every peripheral. The other thing that this does is it gets them using or relying on the data sheet a lot more. So when you see the options that are presented to you graphically in MCC and you don't understand them, you can go to the data sheet to find out what each of those options means. And if you want to, then directly, manipulate the bit patterns to get it to do that. And then the only thing that might be different if you have an advanced course is that you're now really forcing them to understand that if you're in the industry and you're developing a product, you're going to have to make sure that it's meeting performance and cost constraints. And so the trade-offs at the system level in order to lower cost or to increase the simplicity for maintenance, and also at the software level, the what a production level type of code looks like. So this is now where you're making sure every bit counts, that you're not being sloppy about loops that take up MCU time and so forth. And so it's a much more in-depth overview of the microcontroller as well as the system level integration. And again, now you're at the device level, so you want to use breadboards, or in some cases even a custom printed circuit board to either jumper or solder from point to point with the peripherals. You can still use the generated C from a MCC type of tool, but you'll probably want to show them how to do optimization. So look at the code that's generated, and in some cases, maybe take one or two of the areas and rewrite them in assembly language, or rewrite the C for an optimization. And so now again, it looks more like a traditional approach. The thing that continues to keep it in the makerspace is you're still working towards some sort of final project. You want the end result to be a working system, total system. And in this case, it'll be that balancing robot that follows a line. So you're using all the same peripherals, you're using the same microcontroller, number of different approaches for going at it. So we have a lot of options here that we're looking at, and we're hoping to get some feedback from you on what you think probably either the most popular approach for your school would be, or what elements of these approaches are the ones that resonate the most. Before I go into that open discussion, something that may have been missed when we went over the Curiosity Nano is that we have the Arduino development environment allows you to create libraries for boards that are not made by Arduino. So those are called core libraries for different boards. We have core libraries for those particular Curiosity Nanos that Ross mentioned. And so what that means is once you install that library into the Arduino IDE, you can program the Curiosity Nano the same way you program an Arduino board. So it's the same level of abstraction. But now, if you actually adopted the Nano, you can grow that Nano through every one of these courses. So you can use that same Nano to develop in Arduino. You can use MCC. You can go from using printf statements through import into the MPLAB X development environment and go into a more detailed traditional debugging with the onboard debugger on the Nano. And you can write it bare metal for that device as well. So that's the reason we're selecting Curiosity Nano family for this, for consideration, this approach, because at some point we may actually have solutions to all of these options, and we can base them all on the same device, and then you'll have a choice on how to use it and where to plug it into your curriculum. So with no further ado, I'd like to open it to discussion. We got about 15 minutes, I think, left to the session. And so questions, comments, anything here resonate?
Dave, could you share the that one slide on the screen again so that we can talk to that?
YC, do you have that cricket sound effect that we were using earlier?
No.
Has
So
anyone used a project-oriented approach in any of their existing curriculum, or are they currently using that? And how does that differ from maybe what we've presented?
Anybody wants to provide David and Ross any feedback, and go ahead and unmute yourself and state your question or your concern or your position.
Okay.
Dave, I
So
just want
maybe
to
if
add.
I ask the question a different way, has your school outlawed Arduinos? When I attend the ECEDHA conference every year, there's always kind of mixed opinions about whether Arduino has any place in a undergraduate or graduate education. And in a lot of cases, the schools have prohibited the use of Arduino for capstone projects, for example. I know when Microchip goes to hire students when they graduate, we're not averse to seeing Arduino projects, but if that's all they have, we probably are not likely to hire them unless they also prove some understanding of the underlying concepts and capabilities of the processors. So I don't know what your experience has been or what your position is on how or where to use Arduino in the curriculum. It makes it easier for us if we can go straight to the Nano with MPLabX, because then we're avoiding any of that cross-platform stuff, and it also gets them into the microchip tools more quickly. But we're trying to get some feedback on whether to address these more fundamental approaches as well.
Dave, one comment on that last slide that you showed. I think you showed the perfect divergence in the purpose of a coursework like this, whereas on one side you have retention and the intro to embedded curriculum, which helps incoming students. On the other side, you have the more advanced topics or the deeper dives into microcontrollers, and I think this breakdown or this divergence here is actually something we see a lot in academia. For the people who are on the call who are from universities, correct me if I'm wrong, but I think from a department level, they will be worried more about retention and introduction of the embedded microcontroller or embedded design concepts to students as early as possible. I think the first two line items to that would be perfect for departments. The last two line items would be what industry is looking for, or how do you better prepare students for the industry. So in my opinion, I think a good middle ground is that foundational introduction type coursework where you start digging into the concept of an embedded design coursework, but it appeals to a broader base audience, which helps the university perhaps not scare away people who are coming into an electrical engineering curriculum, and giving them a sense of understanding as in, you're an electrical engineer and this is what you are going to be designing for, a potential career path. So I think there's a very strong case for the foundational introduction type coursework, and maybe the one right below it where you're talking about the more comprehensive introduction to microcontrollers. So you can have the foundational in the beginning. Thank you so much. I'm going by memory here, and the comprehensive coursework in the middle. And I think we have a couple of. I think Kevin here has feedback here. Kevin, do you mind if I read your comment, or would you like to
you
jump
can read
in?
it or I can talk. I was just commenting. We have a general engineering program, and so we use the Arduino and the plugins and the higher levels of abstraction when we're not dealing with ECE students. So when we're training a mechanical engineer or a chemical engineer, which is 2/3 of our students, that's where that comes in really handy. And we can get them designing microcontroller based stuff in that class. And then later in the curriculum here, the double E's go into, and we actually use Texas Instruments for that, but we go into the more bare metal type thing that you guys were describing with a lot of predefined structure and headers and things like that. So we actually use both depending on who our audience is.
Thank you, Kevin.
Gleb,
would you like to chime in, or?
Yes, please. Thank you very much for a wonderful presentation. I'm Gleb Chislavsky. I work for Lamar University. Happen to teach embedded system, I guess, course. I have a, maybe a strange question, but we were always looking at this course as the opportunity to introduce students to really low-level programming language such as assembly, because we always felt that it allows us to kind of go deep into architecture. In all your examples, you're using fairly high-level Arduino language and something else. In your opinion, should we say that assembly language is a dinosaur that, basically nobody needs anymore? Just wanted to ask your opinion. Thank you.
So yeah, it's a good observation, and we haven't ignored assembly language. So in the third line there, where it's more of a traditional introduction to microcontrollers, you want to expose the architecture, the instruction set, the addressing modes, all of that, as well as the underlying hardware programming. And so in that course, you might want to do assembly language. What I'm seeing a lot of is even the schools that don't want to leave assembly language are starting to adopt some form of C on top of that. I know our customer base is pretty heavily, into C. Most all embedded programming right now is being done in C or C++. And the folks that are developing the low-level drivers still need to write it in assembly. The folks that are critical performance or responsiveness are still writing in assembly. So the students, I think, need to understand that there is a time and a place for the assembly language and the advantages that it gives you over C. And so you can create, some activities. And the intent here, if we develop that course, would be just that. We would, show some introductory functionality in assembly. We then probably quickly move to C to get them through the majority of the course. And then at the end, go back to assembly language to say, all right, here's some of the C code that either you wrote or was generated. And what you need to do is reduce the interrupt latency time, or you need to improve the performance, or you need to offload the microprocessor from something. And it forces them to rewrite the same functionality down in the assembly language. And I think what that does is it then makes them more sensitive and more appreciative of where the time and place is for assembly. So if you introduce a little bit of assembly up front, that's good, because you can talk about the control, the architecture of the processor. If you move to C, you can start explaining to them that, the architecture of the processor really isn't that important if you develop in C. Of course, that's not good for microchip, but we're okay with that because that's the way the industry's gone. But again, I agree with you. You do need to make sure if they come out of a double E program in digital electronics with microcontroller experience and have never seen assembly or don't know anything about where its place is, they're probably not as well prepared for the industry. Okay.
Ed Ivory, I see that you have a comment from Portland State University. Would you like to talk to your talk a little bit more about that?
Sure.
Yeah.
So I am I'll be honest here. I suffer from a little bit of imposter syndrome because I'm not an electrical engineer. I'm a mechanical engineer. But I run our electronics prototyping lab program here at Portland State University. And part of that is supporting the Cornerstone and Capstone projects. Cornerstone is a little bit like a 200 level capstone. So they get their hands on a project early on, electrical engineering or electrical and computer engineering, get their hands on hardware at the 200 level as a requirement for the class. We see everything from, embedded, some embedded web API sort of things where they're scraping bus information, like bus arrival time information, to systems that might be a little bit less rigorous, but the students are coming from a less technical background, perhaps. Perhaps they don't have the experience or the curiosity that they needed for that project wasn't fostered previously. And so we might see something like automated watering system, which has been done a million times on the internet, but they're at least getting their hands on something early at the 200 level. And we find that really helps prepare them to do a solid capstone where they can dive deeper down into, they understand those high level concepts like you were talking about. And then they can dive down into the lower level stuff and explore that more in their 300 and 400 level courses. So we find that works very well here, to have sort of a primer for them essentially at the 200 level. And I feel like this is the best job in the world to run a lab like we have, honestly, because I get to see it's just like the breeding of ideas where one idea meets another idea, and then they have another baby idea out of all of that. And it's really just a phenomenal place to be involved with the student success. It's just pretty amazing. But I'm gonna back up because I don't know how to end talking on Zoom still after 3 years of Zoom meetings. Thank you.
No worries. I don't think any of us have really mastered that skill. So, but
Yeah.
I really appreciate you.
Yeah, you make some good points. And in fact, I see
Right.
a lot of that when, most of the capstone projects in schools, they try to create kind of cross-discipline teams. So you'll have a double E and a mechanical engineer and business person and a lot of different folks involved. And when the mechanical engineers can't find a double E for their project, the Arduino is perfect. And so having that introduced to them and making them aware of it makes a lot of sense. And I do see a lot of capstones that are non-double E projects incorporating embedded type concepts into their designs just because they were introduced to the Arduino early on in the curriculum.
But if you have any comments or questions, feel free to reach out to me, Taimia, Kim, or Tom. We will be happy to address them or forward them on to the appropriate parties.
Okay, great. Yeah, and I'd like to just to camp onto that. The meeting chat, oftentimes there are a few other unanswered questions. We're going to get to those, but in addition to that, we'll share the meeting chat with all the registrants, because there's a lot of good ideas amongst everybody, the participants. So we'll do that as well. And then I'd like to once again thank particularly YC, but all the makers sponsors, the DigiKey, Super Microchip Technologies, and then the next upcoming one of our summits will be with Infineon Technologies, and Patrick Kane will be leading the charge there in early 2024 to get ready to tee up for our annual conference. And the thought process there is learn some more about the ever-changing and ever-growing and complex ML AI world. So we'll deal with that in a more specific manner in the early in the year. So thanks again to everyone, all the participants, thanks to the speakers, and particularly thanks to our maker sponsors. And I hope everyone has a great rest of your day.